Hello students, myself Muhammad Adil Sheikh, an assistant professor of Chemical Engineering Department from LJIET Institute of Engineering and Technology. Today I am going to take a lecture of a mass transfer operations 2, and in this video we will see about the experiment that will be including the humidification by using a wetted wall column. Okay, so let us start the video. Now this is a second experiment and the name of the experiment is for the humidification. Now what is a humidification? So basically humidification means increase of a moisture content within the air. Now when we will contact air and water mixture, then some of the moisture, or you can say water particles, will be evaporated into air, and so we can say that the air will be humidified. Alright, now the aim of this experiment. So basically the aim is to study the rates and the phenomena of diffusion into gases flowing through the pipe, and also to verify Sherwood and Gilliland's correlations. Okay, so now this is the instrumentation of the wetted wall column which will be using for the humidification. So this is how a wetted wall column will look like. Okay, now the working principle of the wetted wall column. So basically the wetted wall column is a particularly chemical equipment which is used to achieve mass and a heat transfer between two fluid phases. In general, one phase is gas phase and one is a liquid phase. So this is the working principle of the wetted wall column, that it is a chemical equipment, of course, which will be using for a mass and a heat transfer between the two fluid phases. And here the one fluid will be gas phase and one will be liquid phase, and after contacting both of them there will be mass and a heat transfer between them. So this is how the wetted wall column will actually look like. Now here there will be a wall, okay, and here from the top of the wall the liquid will flow in, and it will be the liquid will be out from the bottom, while from the bottom of this column we will flow the flow of the gas that will be at the center of the column, and the air, or you can say the gas, will be leaving from the top of the column. Okay, and it will be connected with the rotameters for the flow adjustments and also with the heater, so that the gas phase, or you can say air, will be a little bit heated. Okay, now the construction of a wetted wall column. So generally the equipment which is used for this experiment, there is the construction. So the experimental setup will consist of a 35 mm ID of borosilicate glass column of 750 mm length with a proper arrangement to distribute air and water throughout the column. So basically there is a borosilicate glass column which is 35 mm inside diameter and 750 mm of length, and there is a proper arrangement to distribute air and water through this column. Now two sets of wet and dry bulb thermometers have been provided to measure the humidity or partial pressure of the water vapor in air at an entry and at an exit of the wetted wall column. So within this equipment there are two wet bulbs and dry bulb thermometers at inlet and outlet to measure the humidity, or you can say partial pressure, or basically it is to determine the temperature of the vapor at the entry and exit. Okay, then there will be 0.5 HP of monoblock pump with a 50 liter approximate, then SS304, that is a material of construction, that is a stainless steel tank, and have been provided to feed the water at the top of the column through pre-calibrated rotameter. So there is a pump within this wetted wall column, okay, and it is feeded it is provided at the bottom, and this will provide a feed of water at the top of the column, and there is it will be passing through the rotameter. Here the air is supplied with the help of 0.5 air compressor, which is optional, through the rotameter to the bottom of the column. Now here we will be supplying the air through the air compressor, which is and the flow will be passing through the rotameter, so that we can adjust the flow of the air, and the air will be provided at the bottom of the column. An air heater has been provided to heat the air slightly to the compensate boiling effect of an expansion of a compressed air. So basically after passing through the rotameter, the air will be passed through the air heater, which is provided to heat the air. Okay, so this is how the construction of the wetted wall column, and here this is the equipment which is being used for this experiment. As you can see, there is a borosilicate glass tube which is a which is a column, or you can say wetted wall column, and here from the top we will be providing the water, and the water will leave from the bottom, and at the bottom of this glass we will be providing hot air, and from the top of the column the hot air will the cold air will be removed. Okay, there are two rotameters, and also there are temperature indicators which will be indicating the temperatures at the inlet and outlet, and they will give the two temperatures, that will be a wet bulb and a dry bulb temperatures. Okay, now the experimental procedure of this experiment. Now first of all, fill the water tank with a fresh tap water and switch on the pump, keeping the bypass valve totally open. Then open the valve on a water rotameter to adjust the flow of water through the column, and if no flow is obtained, slowly close the bypass valve to get the desired flow of the water through the rotameter. Initially keeps high flow rate of the water to obtain uniform distribution of water throughout the perimeter of the column, and then adjust it to the desired level. So basically, first of all we will fill the water tank with a fresh tap water, and then we will switch on the pump so that it will flow, so that the flow of the water will be obtained through this column. Okay, and here we will open the bypass valve totally, then we will slightly adjust the valve. Okay, and through the rotameter we can adjust the flow rate of the water through the column, and if there is no flow of the water through the column, then we will slowly close the bypass valve so that we can get the desired flow rate of the water. Now initially we have to keep the higher flow rate of the water so that we can obtain a uniform distribution of water throughout the perimeter of the column, and after that we will adjust it to the desired level. Now after this desired, or you can say uniform distribution of the water, we will switch on the air compressor, and we will open the rotameter valve so that we can set the flow rate of air at a desired value. After that, after obtaining the desired value of air flow rate, we will switch on the air heater. Then after this we will measure the dry bulb and wet bulb temperatures, that will be indicated by the thermometer located at the bottom and at the top after 5 minutes. So when we will get the desired values of air and water flow rates, after that we will measure the dry bulb and wet bulb temperature, which will be indicated by the thermometers, which is provided at the top and at the bottom of the column. Now after after 5 minutes, now then we will either change the water flow rate or air flow rate, so that we can change the condition of humidity or turbulence, and after that we can take a 4-5 readings in this manner. Alright, now let us switch to the construction and a working portion of this equipment. At first we will see the construction of a wetted wall column. Okay, so now here, as you can see, this is a wetted wall column equipment. Okay, now you can see here there is a borosilicate glass tube. Okay, you can see in a figure. Now this is a borosilicate glass tube. Now here the water will flow downward through the vicinity of the wall, while through this central portion the air will be blown upward. This is a pump which is being used to pump the water through this tube. Okay, now this is a feed tank. As you can see, there is a water inside this. This is a motor, or you can say pump, which is being used to pump the cooling water through this tank via this pipe, as you can see in this video. Okay, through this there is a valve provided here, which is a bypass valve, and now from this the water will flow through the rotameter, and through the rotameter it will be allowed to feed at the top of this column. Now this is the thermocouple which is being installed at the top of the column. Okay, and this is the thermocouple which is being installed at the bottom of the column. This is the air compressor which is being used to provide the air at the bottom of the column. Here you can see this is a meter through which we can find out the air pressure. This is a heater box which is being used to heat the air, and this is a air rotameter through which we can determine the flow of the air. Now we will see the working portion of this equipment of wetted wall column. Okay, now first of all we will start this, and we will arrange, or you can say we will try to find out the air. We will try to maintain the water flow rate. Now this is the bypass valve. As you can see, it is fully open right now, so most of the water is being bypassed through this. Okay, and now we will try to manage the water flow rate through by adjusting the rotameter. Okay, now as you can see here in this video, that the water is flowing through the vicinity of the wall, and we have adjusted the water flow rate. Okay, so this is the water flow rate. As you can see, the water is being flowing through the vicinity of the wall, and it is flowing here, you can see, from the top. Alright, now it is flowing through the vicinity of the wall to the bottom portion like this. Okay, now we have started the air compressor. You can see in this video we have started the air compressor. Okay, and the air is being filled, and we have adjusted the water flow rate by using this water rotameter. Okay, now this is the air compressor. The air is being compressed, and it is being, now we will start open this valve so that we can provide the air at the bottom of this column. Okay, so this is the air compressor which is being connected via pipe. Okay, after this, when we have opened this, the air will flow, and here it is connected to the rotameter. As you can see, the one pipe is at the inlet, and after that the outlet from this air rotameter will be passing through this heater box, so that the air will be heated. Okay, and from the top of that, the heated air will be passed through this blue pipe, as you can see in the video. So from this pipe, the heated air will be flowing down, and it will be at the inlet. Okay, so before inlet through the column, you can see here that the thermocouple is installed. Okay, so that we can have the idea of the temperature, or you can say wet bulb and dry bulb temperatures. So this is the air rotameter through which we can adjust the flow of the air. Okay, right now it is being adjusted already. Okay, now after this we have started the heater switch, so that now the air will be heated, and from the bottom of this column the air will flow through the central portion. Okay, so this is how the water will flow. Okay, and along the boundary of this column, you can see there is a little bit humidity, or you can say humid air, because of this heated air, and this is a thermocouple. Okay, so from this we can find out the inlet and outlet wet bulb and dry bulb temperature. This is a water rotameter, so again we have adjusted the flow of water, and now we will start adjusting the air flow rates. As you can see, through this manner we can adjust the flow rate of air. Okay, so this is the water rotameter, the flow again adjusted at a 10 something, and this is a air rotameter. Okay, so this is how the water will flow now, because of the another adjustment of the water flow rate, and the heated air will be flowing through the central portion of this column. Okay, so this is a portion through which the water will be obtained at the bottom. Now this is the temperature indicators, as you can see. So this will indicate the temperatures of the 4 channels 1, 2, 3, 4. Okay, so this is how you can find out the temperatures. This will indicate the different locations. Okay, the 1 and 2 will be indicating the temperatures of wet bulb and dry bulb temperature at outlet, and 3 and 4 will indicate the wet bulb and dry bulb temperature at an inlet. So as you can see, we have to actually allow this to remain steady at somewhat around 20 seconds, so that we can obtain exact temperatures. Okay, now after each 5-minute intervals we have to take the the readings of these temperatures. Now you can see after some time there will be humidity along with the column boundary. As you can see in the video right now, that the water is flowing, the air is moving upward, but there is some humidity at the column boundary. Okay, now again after some time we will find out that what will be the temperatures at a different channel locations. Okay, so along with the 1 and 2 we can find out the wet bulb and dry bulb temperature at outlet, and 3 4 will indicate the wet bulb and dry bulb temperatures at a inlet, as you can see in this figure or you can video. Okay, so in this manner you can operate this equipment. Now there are some data given to us like a diffusivity or of the water in air at 290 at Kelvin, or you can say 24.85 degrees Celsius, and 1 standard atmosphere, that is equals to 26 multiplied by 10 to power minus 6 meters square per second. And there are for different temperatures the viscosity of air, density of air, the flow, the velocity, and also the density of water and the saturated vapor pressure are given. Okay, now after taking the dry bulb and wet bulb temperatures at inlet and outlet after 5 minutes intervals, okay, we have to draw an observation table. So it will look like this. Okay, the first column will be containing the water flow rate, that is a LPM of QW, then the air flow rate in LPM, then air temperature both at inlet and outlet, and TD1 TW1 at inlet, and TD2 and TW2 at outlet. Now here water flow rate will be in LPM, so LPM is liter per minute, and also the air flow rate will be a LPM, that is a liter per minute. Now here the air temperature at inlet, the TD1 is a dry bulb temperature at inlet, and TW1 is a wet bulb temperature at inlet, and also TD2, that is a dry bulb outlet temperature, and the TW2, which is a wet bulb outlet temperature. Okay, so initially we kept the water flow rate, that is 0.5 lpm, and also the air flow rate at 5 lpm, and after 5 minutes we have taken these readings. Okay, so as you can see after 5 minutes the inlet temperature, or you can say dry bulb temperature at inlet was 31 and wet bulb temperature was 29, while at outlet the air temperature was reduced, that is at a 25 for the dry bulb temperature and 23 for the wet bulb temperature. Now again more after 5 minutes there wasn't much big difference was seen, but after the 5 minutes, or you can say totally 15 minutes, there was a change in a temperature. Like the inlet temperature was increased, that is up to 33 degrees Celsius, and the wet bulb temperature was 32 at inlet, but the dry bulb temperature at outlet was constant, that is 25. Okay, now after that we slightly increased the air flow rate up to 8 lpm. Okay, and for that the inlet temperature was 36 degrees Celsius for the dry bulb temperature, while the wet bulb temperature was 34 degrees Celsius. Then the outlet at the outlet temperature of air, that is a dry bulb temperature at outlet was 30, and the wet bulb temperature was 29. Okay, so this is how we can take the different temperatures for the different water and air flow rates. Okay, now the calculation portion. So for the calculation, the length of the tube which is given, that is 750 mm, then the internal diameter of the tube was 35 mm. So we can find out the wetted surface within a column, that is a meter square, which is a pi dl. Now after that we can find out average temperature of an air, that is a T average, which is equals to TD1 plus TD2 upon 2. Here TD1 and TD2 are the inlet temperature of air and outlet temperature of air, but these are the dry bulb temperatures. Then the air flow rate in kilomole per second will be equals to air flow rate in LPM multiplied by 10 to power minus 3 multiplied by 273 upon 273 plus TAV multiplied by 1 upon 22.41. Then after, the total pressure within a column, which will be at atmospheric pressure, and so PT will be 101.3, that is kilonewton per meter square. Now the partial pressure of water vapor in air at inlet, that is a PA1, it will be equals to percentage saturation upon 100 multiplied by PA out. Here PA out will be vapor pressure of water corresponding to the outlet temperature, that is a T out. And here we can find out the percentage saturation from the psychrometric chart. Similarly, the partial pressure of water vapor in air at outlet PA2 will be equals to percentage saturation upon 100 multiplied by PA in. PA in will be vapor pressure of water correspond to the inlet temperature, that is T in. After this, we can calculate the driving force at inlet of the air at a bottom, that is a PW1, which is equals to PA out minus PA1. And here PA out will be pure component vapor pressure of water at a outlet water temperature, that is T out, and PA1 will be partial pressure of the water at a bottom. Driving force of an outlet air at a top will be PW2. It will be equals to PA in minus PA2, where PA in will be equals to pure component vapor pressure of water at inlet temperature T in, and PA2 will be partial pressure of the water at a top. Then mean driving force will be delta PWM, which is equals to delta PW1 minus delta PW2 upon ln of delta PW1 upon delta PW2. Now after that, we can find out the amount of water which is being absorbed by the air, or you can say the amount of water evaporated along with the air. So that will be given by NW, which is equals to QA into PW2 minus PW1 upon PT in kilomole per seconds, and here QA will be kilomole per second of air flow rate. Now here, in terms of mass transfer coefficients kg, the rate of mass transfer will be given by NW, which is equals to kg into A into delta PWM. So from this equation we can write down the equation of kg as NW upon A into delta ppm, which is in kilomole per meter square into second. Okay, now from the equation we can calculate the value of kg for each readings. Okay, then we can calculate the Reynolds number, which is Re, which is equals to D into QA upon ACS into mu of air. Now ACS, which means the cross sectional area of the column in meter square, that we have calculated. Then D is the diameter of the column in meter. QA will be air mass velocity in kg per second, and mu air will be viscosity of air in kg into meter per second. Then we can find out the Sherwood number, that is SH is equals to kg into ppm into RTL upon PT DAV. Kg is a mass transfer coefficient, then ppm is a log mean partial pressure of air, R will be universal gas constant, then T is the average dry bulb temperature, L is a length of the column, PT will be total pressure inside the column, eventually it will be atmospheric pressure, then DAB will be diffusivity of air at average dry bulb temperature. Okay, now after that we can find out the Schmidt number, SC will be mu of air upon rho of air into DAB. Okay, mu of air and rho of air will be viscosity and density of the air at a average dry bulb temperatures. And now from this equation we can find out we can verify that whether the Sherwood number, the equation which is SH is equals to 0.023 into Reynolds raised to 0.8 Schmidt raised to 0.33, whether it is correct or not. Okay, so from this calculation we can find out that whether the Sherwood numbers correlation is correct or not. Alright, now the result of this experiment is that the air after contact with the cooling water, or you can say the simple water, then it will be humidified after a mass and a heat transfer. Okay, so we can say that when we will contact air and water, so the mixture then the air will be humidified. Okay, so this is how we can perform the experiment of humidification by using a wetted wall column. Okay, thank you.